Hello everyone. I believe you are well. Welcome to the session for tonight for for physical science, where I will take you through work energy and power. Hope you will enjoy this session. Let me share the slide. Right. What I will do in terms of this paper of work energy and power, I will just take you through on how to solve problems, especially when you are dealing with work energy and power. Let me zoom the paper. All right. This is the work energy and power question. Then I want us to go through the questions. It says a remote controlled car is driven up. A remote controlled car is driven up. An inclined plane, a remote controlled car is driven up and inclined plane, it is driven up an inclined plane at an angle, at 30 degrees to the horizontal. So they're saying that this inclined plane, it is at an angle of 30 degrees with the horizontal, as shown below. So what they're trying to say, they're saying that this remote car is being driven up. It's moving up in that direction at an angle of 30 degrees at an inclined plane that forms an angle of 30 degrees with the horizontal. This is what we are given. So the object is moving upwards. Right, then now, a car of mass 4 kg. So we are told that this car has a mass of 4 kg. Experience an average forward force. Experience an average forward force of 80 Newton. So which means this force is actually an applied force. Can regard as an applied force. Then a frictional force of 15 Newton. A frictional force of 15 Newton is acting on the car as it moves, So it means this frictional force, we're going to call it a kinetic frictional force, has a magnitude of 15 Newton. And we also have a force applied that has a magnitude of 80 Newton. So this is what we are actually given. The speed of the car at the bottom of the inclined plane is 3 meters per second. So we're given the initial speed as 3 meters per second. Then this is what this is the information that we are given. Now, looking on this question in terms of work energy and power, we need to familiarize ourselves with the following formulas, okay? I apologize, guys. So now what we're gonna do is we need to first understand what we're actually given in order to solve the problems relating to work energy and power. All right, number one, we know that when we are dealing with work energy and power, we need to familiarize ourselves with the following formula. The first one is the work done, where we calculate the work done by the force, which says the work done is the force multiplied by the displacement multiplied by the cos of theta. And what is this theta? Theta is the angle between the force and the displacement. So the theta, it is the angle between the force and the displacement. We also have another formula, which we call it the work energy theorem, which states that the net work done on an object is equal to the change in the kinetic energy of the object. So this is work energy theorem. it's very important to be able to know this work energy theorem formula. And another one, it is that one where we said the work done by the non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. This MCA is the work done by the non-conservative forces. And guys, it's very important in the examination to be able to understand or to differentiate between forces that are conservative and forces that are non-conservative. Right, we know that we have two types of forces. We have a conservative force, and we also have the non-conservative forces. Right, under the conservative force, what is a conservative force? A conservative force is the force whose work done by an object between 2 points does not depend on the path taken by an object. In other ways, it is the work done. It is the force whose work done does not depend on the path. It is independent to the path taken by an object. And there is only one type of the force which is actually conservative, which is the force of gravity. So it means an object that has a conservative force only, mechanical energy, it's always conserved. Mechanical energy is conserved. Mechanical energy is conserved. What does this mean? It means mechanical energy is the same before and after. Only when we have conservative force. And what does it mean? It means that the work done by the non-conservative force, it always zero. When we have a conservative force. Whereas there are other type of forces which is non-conservative, whose work done by by those forces depends on the path taken by an object. And what does this mean? It means that when you are dealing with non-conservative forces, mechanical energy is no longer the same. Mechanical energy, it's not conserved. So it means mechanical energy before and after, it's no longer the same. And which means that the work done by the non-conservative force is not zero this time around. And most of the example of non-conservative force is friction. And force applied, even a tension also. It's an example of a non-conservative force. So it means when you read the question and you find that we have friction or the object has force applied, you must know that you are having a non-conservative forces, which means already the work done by the non-conservative force is not zero. And someone might say, why are you saying when we have a conservative force, the work done or mechanical energy, it's conserved? What do you mean by mechanical energy, which is the EMAC? Mechanical energy is that it is the sum of the kinetic plus the potential. So when we say mechanical energy is conserved, we are just saying mechanical energy before or initial is the same as mechanical energy final. And remember, I said mechanical energy is the sum, which means you can say EK initial plus EP initial is the same as EK final plus EK initial. I'm saying final, I apologize. This is true only when we have conservative forces. Let's prove this. Remember we said the work done by the non-conservative force is the change in kinetic plus the change in potential. If this work done by non-conservative is 0, look what's going to happen. Remember, this is the change in kinetic, and which is kinetic energy final minus kinetic energy initial. Same applies. This is potential energy final minus potential energy initial. Let's transpose the kinetic energy initial and potential energy initial to the right hand side, to the left hand side, because both are negative. So you're going to have kinetic energy initial plus potential energy initial, which is kinetic energy final plus potential energy final. You see that this is the same as the Emac initial, and this is the same as the Emac final. You see that it's now attesting to what I was saying here, to say only when you have a conservative force, mechanical energy before and after will be the same. So it's very important when you're analyzing the work energy equation, you check. Once you read the question, then they tell you that you have frictional force or you have force applied or you have tension. You must know that this is an example of a non-conservative force, which means mechanical energy before and after, it's no longer the same. The mechanical energy is not conserved anymore. So it's very important to understand that. Which means from this question, since there is frictional force and since there is force applied, these are examples of non-conservative forces. Then we'll conclude by saying the work done by non-conservative force, it's not 0. Because these two forces are actually the non-conservative force, which means the work done by the non-conservative force this time around, it's not 0. Frictional force, it's a non-conservative force. And this one, it's also a non-conservative force. Why are they regarded as non-conservative force? It's because their work done, when you calculate their work done, they depend on the path taken by an object. That's why frictional force decreases the net work done on an object. Force applied increase the net work done on an object. So it means it causes work done before and after not to be the same. Right. Then now let's deep dive into the question and try to solve this question, right? Right. According to this, they're saying we are told that there is frictional force, there is force applied. Already we know that these are examples of non-conservative forces. And since they are example of non-conservative force, it means we know that since we have non-conservative forces that are present in the system, mechanical energy before and after, it's not conserved. It's not the same. And these are actually multiple choice questions. So it's very important to understand what you are dealing with. Okay? I believe you guys are following. Right. Then now, let us look on the question. The question says, use energy principle. And this is very important, guys. Use energy principles to calculate the speed of the car after it has traveled a distance of 5 meters up the incline. We are told to use the energy principle. What are these energy principles? The energy principle is just the work energy theorem, or the formula that I just explained out, the work done by the non-conservative force. These are the energy principles. So which means if we use any of the two formulas, we'll be able to get the answer. So if we use the formula for work energy theorem, or we use the formula for work done by non-conservative force, answers will be the same. So these are called energy principles formula. Remember, energy is the ability to do work. That's why when you calculate work done, it's the same as when you calculate energy. They're all measured in joules. So we need to use one of the two formulas. And now, how are we actually going to solve questions? We want to know, okay, fine, what are we given here? We are given delta x. It's 5 meters. We are told that it has traveled the distance of 5 meters, which is our delta x, ladies and gentlemen. Now, because we are dealing with an inclined plane here, first of all, we have to identify forces that are actually acting on this car. I hope you understand what you mean by frictional force. Frictional force is the force that opposes the direction of motion of an object, and it acts parallel to the surface. So we already know that. Now, I want us to first use the first formula to calculate the final. Actually, we have the initial, want to know the final. So let's use the net work done on an object. I'm saying, let's use the work energy theorem to calculate the final velocity, or the speed actually, the speed. It means here we just want the magnitude, no direction. So, okay. In the meantime, let me try to share another slide so that I stop sharing this so that we do it on the other question, because already I have all the information. Let me stop sharing here. Okay. Let me share. Okay, apology, guys. Okay, now I want to share this. Okay, let's write all the information given. Okay. Okay. Okay, now let's, I want to try to reduce this size. Okay, so what do we have there? The object has a mass of 4. Let me write all the information. The mass of the object is 4 kg, if I'm not mistaken. The initial velocity is 3 meters per second. The forward force, which is the force applied, I can just write Fa. It's the 80 Newton. And the frictional force, let me call it kinetic friction. What is the magnitude? 15 Newton. And we are told that this is at an inclined plane. That forms an angle of, oh, apology, guys. Okay. Okay. Okay, this is what we have. Okay, let me draw it nicely. Okay, I believe you can see it. Okay, let's just say this is, let me use a different color. Okay. Yeah, there is our object. First, we need to identify forces that are actually acting here. Then we're gonna have the force applied. Okay, let me just put it there. So this is our FF, which is this one. And we also have frictional force, which is the force that opposes the motion of an object, and it acts parallel to the surface. And we also have the normal force, which we know it does not do any work. It does no work on an object because it acts perpendicular to the displacement. And since we are dealing with an inclined plane, it means we'll have a force of gravity. That will be, the direction will be this side due to the slope. So this is our FG. And we know since this is the FG, it means the angle here, the inclined angle here, 30 degrees is the same as this one. So let me use just a different, just to represent this, because I want us to solve questions relating to this object here. So this is the 30 degrees. So what you can do is, it's either we resolve the force of gravity into components, or we can also calculate the work done by the force of gravity by looking at the, by just looking at the force of gravity without considering the components. We can do it in two ways. There's no problem. Remember, we are being told that the object it's being pulled up, which means this is also the direction of the delta x. Or we are also told that the delta x here, it's 5 meters. Okay, let me just confirm something. Remote 30 degrees or 4 kg, 480, 15 speed. Okay, fine. And everything is okay. We want to calculate the final velocity. So what do you want to find? We want to calculate the final velocity. Right, we can do this in many ways. Number one, what we can do is we can say, remember I said I want us to use the work done by the work net, the work energy theorem, which says the net work done is equal to the change in kinetic energy. So what we can do, maybe method number one, let's calculate the net work done on object. The net work done on object by each force. By each force. So for now, I will not consider the normal, because I know if we were to consider the angle between the normal and the displacement, it will be an angle of 90 degrees or 270, and cos of 90 is 0. That's why we say it acts perpendicular to the surface. So we're not gonna, to the displacement. So we're not gonna consider the work done by the normal force. And what you're gonna do, you're gonna say, okay, fine. Let's calculate the net work done by each force. Actually, let's calculate the work done by each force, then we calculate the work net. So it means what I want to get, you must get this first. So to do that, let me use a different, then we're gonna say the work net, it is the work done by the force applied plus the work done by the frictional force plus the work done by the Fg, which is the force of gravity. Now I'm not resolving Fg into components. So to calculate the work done by each, what I will do, I will use this. Okay, let me write, apology guys. So I wanted to calculate the work done by each force. To do that, you can use this formula. Work done is equal to force delta x cos of theta. So initially I can say the work done by the force applied. It means I just replace this, the F by force applied. So it will be force applied delta x cos of theta. What is the force applied? The force applied is 80. And this object has traveled a distance of 5. And now we have to consider the angle between the force applied and delta x. Remember, the object is moving upwards, so it means this is the direction of the object, delta x, and this is also our force applied. And what do you want? You want the angle between the delta x and the force applied. And since the lines are parallel, it means the angle between them is 0. So now we're gonna multiply this, and 80 multiplied by 5, I think this will give us 400 joules. So the work done by the force applied is actually 400 joules. Now we have to calculate the work done by the friction. Same applies, which is the frictional force, delta x cos of theta. The friction is 15, that delta x it's 5. Cos of, what is the angle between friction and the displacement? Remember, the object it's being moved upwards. It means this is the direction of the delta x. And the frictional force opposes the motion, which means it moves in the opposite side. So what is the angle between? It's 180 degrees. So we're going to put 180 there. And this will give us how much? So this one will give us a magnitude of 75, or actually negative 75 joules. Now we have to calculate the work done by force of gravity without considering the components, which will be Fg delta x cos of theta. And what is Fg? Fg, we know it's mg. So it will be mg delta x cos of theta. And let's do the substitution. This will give us the, let me just write it here. The work done by Fg will be, what is the mass? The mass is 4 by 9,8 by 5 cos of, I want the angle, guys. We want the angle between force of gravity and the displacement. And look at this, guys. It's very important. Look at this. If you look on this object here, this is my for Fg. And this is my Fg. Where is the object being moved? It's moving upwards. So it means this is our delta x here. Okay, let me use a different, it's fine. If that is our delta x, we want the angle between the Fg and delta x. Obvious, here, the angle is 90. So we're going to add 90 with 30. So 90 plus 30, this gives us 120. So it means the angle between the displacement and the Fg is 120 degrees. You see, we resolve this without, like, I wanted to calculate the work done by the force of gravity without having to resolve it into components. Because some can first do we can resolve the Fg into components. So we're going to use tail to head and tail to head. So we're going to have Fg perpendicular and Fg parallel. Obvious, the Fg perpendicular, it does not work on an object, because the angle between the displacement and the Fg perpendicular will be 90, will be this angle here. So to avoid that, it's still fine. You can also use that. There's no problem. So let's solve that. It's 4 multiplied by 9.8 multiplied by 5. This will give us 196. Then we're going to say 196 cos of 120. So this will give us negative 98 joules. So this is another way of calculating the work done by the force of gravity without having to consider the components. But still, you can still resolve your expression to components. The answer will still be the same. So you're going to say the work net on an object. What is the work done by force applied? It's 400. What is the work done by frictional force? It's minus 75. And the work done by force of gravity, it's negative 98. And why the work done by force of gravity is being negative? Is because when we resolve the Fg, the force of gravity, into components, it will give us Fg perpendicular and Fg parallel. And the only components that is doing work on the force of gravity is the Fg parallel, not this, because it acts perpendicular displacement. But the Fg parallel, it actually moves in the opposite direction of the object. So it's moving downwards. And delta x, so the angle between them is going to be 180. That's why here, that's why we are getting negative. Even if we resolve, let's say we resolve the Fg parallel. Fg parallel will be mg what? Mg sine 30. And what is our m? Our m is 4. Our gravitational acceleration is 9 sine of 30. Sine of 30 is half. And 4 multiplied by 9.8. Half of 4 it's 2. And 2 multiplied by 9.8, this will give us 19.6 Newton. And if we take that 19.6 Newton, we multiply by the displacement, which is 5. And we multiply by the cos of 180. It will still give us negative 95. You see that whether you use components or you don't use components, the answer will still be the same. I believe you guys are following. I believe you are following, ladies and gentlemen. So let's now calculate the net work done on object. It means the total work done on this object, the net work done on this object would be 400 subtract 75 subtract 98. This will be 227 joules, if I'm not mistaken. So since we know this, we can now use the work energy theorem to calculate the final velocity. Okay? We know the initial, then now we can calculate the final velocity. And to do that, it means, let me try to erase some things here. We can say, since we know that the work net on an object is equal to the change in kinetic energy. So we can now work it like this and say, okay, guys, apologize. Okay. Now we can say the work net is change in kinetic energy. We know the work net is 227. And what is change in kinetic energy? It's kinetic energy final minus kinetic energy initial. So I can now erase this so that we have more space to solve our equation. So now this would be 227. Kinetic energy is just half mv squared, but because it's for final, so we're going to say final minus half mvi squared. So we know the work net. Now we can substitute the mass, it's 4. Same applies here, the mass is also 4. What is the initial speed? It's 3. So we can have 227. Half of 4 is 2, final velocity squared minus. So we're going to have 0.5 multiplied by 4 and multiplied by 9, 3 squared. So this will give us 18. Then we transpose, because 3 squared is 9 and 4 times half of 4 is 2 times 9 is 18. So we can transpose 18 to the left-hand side. So it's 227 plus 18. So this will give us 245 equals to 2vf squared. Then we divide everything by 2. So the vf squared will be divided by 2. This will be 122.5. Then we put the root sign. Then what is the final velocity? So the square root, the root of 122.5. The root of 122.5 is 11.07 meter per second. 11.07 meter per second. That is the final velocity. It is the final velocity of an object. I believe you are following. I believe you are following. Remember, they said use work energy, use energy principle. Here we use work energy theorem to get the answer. So how about if we do not want to use work energy theorem? So it means we can use the other formula, as I said. So now, what we can do is, okay, let's use another method to check if, yeah, just to check if the answer is the same. Remember, it's not about saying, I like this formula, I have to use it. It depends with the question. Sometimes you find that the question is easier when you use work energy theorem, or the question becomes easier when you use the other formula. So it's very important to know both of them. And this is not the only way of calculating by using work energy theorem. We can calculate, actually the forces that are actually doing work here are the horizontal forces. So we can calculate the net force of the horizontal forces, then we work out with the displacement, then to calculate the work net, which means using this formula without having to calculate the work done on each. So if we calculate, we use this and say work net is the F net multiplied by delta X. It will still give us the same answer. But now I want us to calculate the work, to answer the question using this formula. The work done by the non-conservative force formula. And guys, it's very important to be able to know which forces are non-conservative. Looking on the question, we must first calculate the work done by non-conservative. The work done by non-conservative, it's only force applied there and the frictional force, which are non-conservative. So it means we're going to combine the two. We're going to say it's the work done by force applied plus it is the work done by friction. These are the non-conservative forces. But already we have calculated this. There's no need us to repeat what I said earlier. So this is 400. This one needs 75. We already know this. So now we're going to say 400 minus 75. Then it means the work done by the non-conservative force is only 375 joules. You see that the force applied increases the work done, the frictional force decreases the work done. So among that, we're going to say the work done by the non-conservative force. Okay, let me write it this side. Actually, let me just erase this because I want us to do something here. So it's very important to know which forces are non-conservative. It's not about cramming, pass and forget. You need to understand what you're doing. Then it will be easier for you to answer questions in the exam. I apologize. Okay, so now we're going to say, right, the work done by the non-conservative force is the change in kinetic energy plus the change in potential. Work done by non-conservative change is just kinetic final minus kinetic initial. Same applies with potential. Potential final minus potential initial. So let's work out this. What is this is half mvf squared, half mvi squared. What is the formula for calculating potential? Potential is calculated by using mass, gravitational acceleration, and the height. So this will be the mgh final minus the mgh initial. Let's do the substitution. But now, before we do the substitution, guys, it's very important to understand something. Let me take you back to the diagram. In the diagram, ladies and gentlemen, this diagram given is the same as a right angle triangle. So we are given an angle here. We are told that the angle here is 30 degrees. And the object moves from this. We want to calculate the final velocity here. We know the initial is 3. And the object will travel a distance of 5. Which is actually our displacement. So remember, when we are using this formula, you need to know the height final and the height initial for you to answer this question. But look, if the object, when the object was there, it was at a height of 0. So it means the initial height is 0 because it's moving up. So we want to know what is the final height here, this height, when the object is here, because it moves at a distance of 5. So you see that we can get this height because this is a right angle triangle by using Socatrua. To do that, we look at the angle. This is the opposite. This is the hypotenuse, the longest side, and this is the adjacent. So we have to calculate the opposite, which is the height, by given the hypotenuse. So we're going to use sine. So we're going to say sine of 30, it's opposite over hypotenuse. And what is the opposite there? The opposite is the h. The hypotenuse is the 5. So it's over 1, then we cross multiply. The h will become 5 sine 30. Sine 30 is half. So half of 5 is 2.5. So it means now we know the final height is 2.5 meter. The initial height, it's 0, the final height, because it's moving from bottom to top. And sometimes they can give you this with the angle, you can determine the displacement. I believe you guys are following. All right, let's move on, ladies and gentlemen. What is the work done by non-conservative force? It's 325. We know the mass is 4, so we're going to say half into 4. Final velocity, we don't know. Half into 4. Initial velocity, we know is 3. Plus mass is 4. Gravitational acceleration 9.8. What is the height final? Height final is actually 2.5. We got it now. Mass is 4. Gravitational acceleration is 9.8. What is the height initial? Height initial is 0. So we'll have 3, 2, 5. Half of 4, it's 2. So it's 2 final velocity. Remember this, we said it's 18. Plus 4 multiplied by 9.8 multiplied by 2.5. So this will give us 98. And this guy will be 0 here. So working out this, we're going to have 3, 2, 5 minus, why minus? Remember, minus 98 plus 18 will give us 80. So this will be 80. And since we have 8, we can transport it to the left-hand side with minus 80. So we're going to have 2 final velocity squared. 325 subtract 80. This gives us a value of 245. Then we divide both sides by 2. Okay, I apologize for saying therefore. Dividing by 2 obviously will give us 122.5. Then we apply the root sign. So the final velocity or the speed will still be 11.07. So it's 11.07 meter per second. See that the answers are the same. The answers are the same. So it actually depends with the question given. If you are using this formula, the potential will require you to know the initial height and the final height. I believe you guys are following. Okay. Let me share and the initial, the first slide. So we are done with this one out of 7 marks. We have answered the question. The final, the speed of the car after it has traveled 5 meters, it's 11.07 meter per second. Now here is the second question. And after that, we have the third one. So we actually have 3 questions to look at. Okay, here I want us to just go through the question. I'll read the question with you. Then maybe for some time, then I'll just give you an activity just to answer the question for me. Then from there, we'll do the corrections together. A 2 kg block, a 2 kg block, a 2 kg block. Okay, a 2 kg block. So it means this block has a mass of 2 kg. Initially at 4 meter high, it's very important. Initially at 4 meter height, which means initially at the height of 4. Is released and slides downhill from rest on the frictionless. This is very important. You must read the question and understand. So it means the object was here. This point. And this object was released from rest, was released from a height of 4. It means from here to here, it is 4 meters. So we can regard this as the initial height because the object is being released from this point. It is released from rest, which means we also know the initial velocity of this block. So the initial velocity is 0. But guys, you need to read the question, understand? It's released and slides. When we say something is sliding, it means there is no force applied. It means the force applied here is 0 Newton. Because it's just sliding. From rest on a frictionless ramp. There is no force applied and there is no friction. It's 0. 0 force applied, 0 friction. What does it mean? And it's very important, guys. You need to read the question and understand. It was released from a height of 4 from rest on a frictionless ramp, then moves along a horizontal surface. Or it means up until here. From there, it moves on a horizontal surface. So it means from this point up until here, there is no force applied, there is no friction. And we know these are non-conservative forces. So which means that from this point to this point, is mechanical energy conserved or not? I want you to tell me the answer. I'll just give you some few times for you to decide whether whether mechanical energy is conserved or not, from the top of the ramp to the bottom up until here. Obvious. I believe you have the answer. Since the force applied is 0 and the frictional force is 0, it means the work done by the non-conservative force is 0. And since the work done by the non-conservative force is 0 here, it means mechanical energy is conserved. Mechanical energy is conserved. It means it's the same from the top of the ramp to the bottom. Now, let's continue. It means, I'll write here, the work done by non-conservative force is 0. Here, just from here, because there's no force applied. Okay? And then moves along a horizontal. It moves along horizontal. It then moves on a 10 meter from this point and this point. It moves a 10 meter, which is actually the displacement. Length, rough horizontal surface. So it means from here to here, there is friction here. There is frictional force. And remember, the object is moving to the right, and frictional force needs to oppose. Okay, it's supposed to be straight, but I believe you can see it. So there is frictional force between, like, from like where it moves a distance of 10 meters. There is frictional force. And we know frictional force is a what? It's a non-conservative force. Okay. So it means from this point up until here, the work done by non-conservative force, it's no longer 0, which means mechanical energy is not conserved. And we are told that a rough horizontal with coefficient friction of 0.2. So it means from this point to that point, where it moves a distance of 10 meters, it was having a coefficient of friction of 0.2. And we know once they give us the coefficient of friction, then we have to calculate the frictional force by using which formula? Frictional force, it's multiplied by the coefficient of friction multiplied by, it's equals to the coefficient of friction and the normal force. So we have to use this formula to say Fk, if the object is moving, it's mu k times the n. The n is the normal. We already know this, so it means you have to get the normal force. Until reaches a rough ramp with the same coefficient of friction and slides a distance of 5. So it means still from this point to this point, there is frictional force also. And this frictional force, which is here, is still having the same coefficient of friction. The coefficient of friction from here and there are the same. It does not mean that the frictions are the same. It's just the coefficient of friction. Mu is 0.2 also there. And it slides on a 5 meter until stop. So you see that from this point here, up until this point, until stop, which means the final velocity is 0. Mechanical energy is not the same from this point up until there. I hope, guys, you are following. I hope you are following. So you must read the question, understand it. Read the question and understand it. Then the first question says, state the law or the principle of conservation of mechanical energy. We know in an isolated system, mechanical energy remains conserved or remains constant. In an isolated system. I believe you know what is an isolated system. We have answered the first question. 2.2, it says, use the law of conservation of mechanical energy to calculate the speed of the block at the bottom here. We want to know the final speed here. At the bottom here. Guys, I want you to pause the video and solve the equation on your own and check what is your answer. Right. Without wasting time, I will have to do the questions, but please make sure that you can also pause. You solve it on your own, then you check the answer, or you check what I got with yours. So here we can do this. We can say, okay, fine. We know that from the top of the ramp to the bottom, there's no force applied. There's no frictional force. It means the work done by non-conservative force is 0. So it means we can use this formula to say work done by non-conservative force, it's change in kinetic energy plus change in potential energy. But since there is no force applied and there's no friction, there's no non-conservative, so this is 0. Which is the same as saying Emeg at the bottom is the same as the Emeg at the top. It's still the same. So it's Ek plus, minus changes, guys. I apologize. So we're going to have minus. So it's Ek final minus Ek initial plus Ep final minus Ep initial. So what is Ek? It's half mvf squared final, half mvi squared initial, mgh final minus mgh initial. This must be equal to 0 for the work done by non-conservative. So let's substitute the mass here. It's 2. We want the final velocity. The mass is also 2. The initial is 0 from rest. The mass is 2. The g is 9.8. What is the height final? Here. The height final is here. So it's 0 this time around. Minus into mass is 2. G is 9.8. What is the height initial? 4. Height initial is 4. We have it. Let's do the working, guys. I will transfer this expression this side. Half of 2 is just 1, so this will give us Vf squared. This part here, because of the 0 speed is 0, so that becomes 0. Even this will become 0. So we're going to remain with minus, how much? 2 multiplied by 9.8. I left my calculator in the office. So we have 2 multiplied by 2 multiplied by 2 multiplied by 9.8 by 4. So this will be 78.4 equated to 0. So we can transpose that VF squared is 78.4 square root and square root. So what is the final speed? So we're going to find the square root of 78.4, guys. So this will give us 2.90. If you are rounded to this map is 2.90 meters per second. Okay, no, sorry, I apologize, 78.4. It's not 2. It's just some typing error, guys. 78.4, it will give us 8.85. I apologize, guys. So it's 8.85 meters per second. So it means the object, the block at the bottom of the ramp, it was traveling at the speed of 8.85. So it means it continued with that 8.85 up until this point where it experienced a rough surface, because it means on this other part the surface was still smooth. So we got the answer, it's 8.85 meters per second. All right, then now it then stays, is the third question says state work energy theorem. I think I've explained that. We can proceed to the next one. Use work energy theorem. You see that they are being specific here. Use work energy theorem to calculate the speed of the block when passing point B here. When passing point B. We are using work energy theorem, not any other formula, but work energy theorem. So let's solve that. Let's solve that, guys. Okay, I believe you are following. Okay, to do that, we're gonna say when the block passes point B, it moves a distance of 10 meters. And by the time it was moving a distance of 10 meters, it was coming with a speed of 8.85. So it means, yes, this was the final velocity, but now it will become the initial. So we're gonna say, right, here, the initial velocity, it was the final, but now it will become the initial. The initial, it's 8.85. We want the final when it was here, where it moves a distance of 10. But they say use work energy theorem. They know you can use other methods. You can use any other method. But here they're saying use work energy theorem. Right, we are going to identify forces that are acting on the object while it was on that rough surface. Obviously, it was just sliding. The only force that is taking place there is the frictional force and the normal force. And the force, they're equal actually. They're actually in equilibrium, they're balanced. Which means for us to calculate the work then done here, okay, work done by normal and FG, it's gonna be 0 here. Why? Why is it 0? Look at the object. The object's moving to the right. So it means the normal is upwards. The object's moving to the right. So it's delta x. What is the angle between this? Is 90. And what is cos 90? Cos 90 will be 0. So it's not doing any work. Look at FG. FG is directed downwards. It's not at an angle. It's moving downwards. And since it's moving downwards, this is our FG. What is the direction of the object to the right? So this is delta x. So what is the angle between? So it's either we use 90 or we use 270. You see cos 90 also, or cos 270 is also 0. It's not doing any work, sorry. So the only object that is doing work here, the only force which is doing work here is the force, the frictional force. So now we're gonna say, right, since they said we need to calculate we need to use work energy theorem, so we're gonna say, okay, fine. The work net is equal to the change in kinetic energy. But now let's calculate the work net first. I think I have alluded this. The work done by normal, work done by friction, work done by Fg. This, it's 0. We have to calculate this. We know how to do that. Fk delta x equals 0 of theta, sorry, plus. What is Fg here? It's 0. Well, I'm saying work done by force of gravity is 0. So you see that the problem here, we know the displacement is 10. The angle between the displacement and frictional force is 180 because the object's moving to the right. Frictional is opposing. So what will be the angle between 180? And since we're using 180, we have to get the frictional force because we're given the coefficient of friction. How and how are we going to do that? To calculate the frictional force, we need the coefficient of friction times the normal. We know this, but we do not know this. And remember, normal force on this object is a vertical force. So we're going to say we're considering vertical forces only. Our vertical forces is the normal and is the Fg, and they're actually balanced. Balance, which means they're in equilibrium because the object's not moving up and down. And since they are balanced or they're in equilibrium, it means the net force that is acting there is 0. I hope you understand. So the normal is positive, is moving upwards, frictional force moving, I'm saying force of gravity is downwards. So we're going to have normal minus Fg equals to 0. So actually we're going to say normal is equals to Fg, force of gravity. And what is the force of gravity? Force of gravity is mg. And what is the m? The m is 2. The g is 9.8. 2 by 9.8, I think it's 19.6 if I'm not mistaken. So now we know the magnitude of the normal force. Now we have to get the frictional force. So using the formula, the frictional force will be, Fk will be mu k. What is mu? Mu is 0.2. Normally it's 19.6. We just calculated it now. So 0.2 multiplied by 19.6, this will give us a normal force, a frictional force of 3.92 Newton. Now we can go and calculate our work net. We have it. So the work net will be, remember, it's just due to the force, frictional force. What is the frictional force? 3.92. Delta x, it moves a distance of 10. The angle between is 180. So it will have a negative work done. 3.92 times 10 times cos of 180. This will give us minus 39.2 joules. So it's a negative 39.2 joules. This is the network done. But it's just that they said we must use work energy theorem, but we can still use the work done by non-conservative force. It will still be the same. The answer will still be the same. Now, let's calculate the speed. So we're going to say we know work net is equals to change in kinetic energy, as I said. And what is change in kinetic energy? Is kinetic energy final minus kinetic energy initial. Then this would be work net, EK final, EK initial. The work net is minus 39.2. That's why it means the final velocity will decrease, because due to the friction, it actually decreases the speed of the object. So we're going to have half mv squared. The m is how much? 2. We do not know the final velocity or the speed. Half mass is 2. Initially, it's 8.85. I hope you understand why we say 8.85. So this will be minus 39.2 plus this answer. Isn't this negative? When you get it, it will be, I'm going to edit that side. 8.85 squared times 2 times half. It will just be 78. 73, 78 point, let's say 0.32. This will give us VF squared. I hope you are following. Then to simplify, let's simplify the expression. Okay, then we're gonna have minus 39.2, if I'm not mistaken. It means the value will be, okay, let me just say 78.32. 0.32 minus 39.2. Yes, this will give us the VF squared. The VF squared will be 39.12, if I'm not mistaken. Then we put the root sign, yeah? Okay, then we put the root, so the root, square root of 39.12, sorry, 39.12. This will give us a speed of 6 point. This will be 6.25 meters per second. You see that the speed has decreased. The speed has decreased. Okay. Like guys, I just want to confirm something. Yeah, everything is fine. Everything is fine. I believe you guys are following. Then now it says use the law of conservation of energy. Use the law of conservation of energy to calculate the height reached by the block. The height reached by the block until it comes to rest. So it means here, they want us to use the formula for this formula. Work done by non-conservative forces, the change in kinetic energy plus the change in potential energy. But we can still use work energy theorem, but let's just use whatever they want us to use. Okay, let me erase this so that we start. But now, okay, I can, isn't it, we know the angle is 12 degrees from the inclined, we know the height, we know the displacement, we know the initial and the final, we know. So what do you want to calculate? We want to calculate the height, or the height by the block until it does that. It's just that, okay, the height, we can actually, I don't know how did they ask this question, but we can actually get the height by using sine. But actually, anyway, let's just use whatever they want us to use, okay? It means now the initial will not be 6.25 from the bottom. Still, there is frictional force. The object has a frictional force also, but it's okay. Since they said they have the same they have the same coefficient of friction. It's okay. Let's just go through it. The angle of the inclined angle is 12. It has moved the distance of 5 meters. The initial, we know it's 6.25. The final is 0. Then we want the height, the h. Okay, let's do that. Let's do that. Right. Well, this is our object. This is our object. So we want side. It has moved it. Okay, the angle is 12 degrees. It has moved a distance of 5 meters. So this is the displacement. Oh, by the way, there is frictional force. We are told that there is frictional force. No force applied. The initial speed from the bottom, we have calculated now it's 6.25. The final, we are told that it is at rest here. We know it's 0, so we want to know this height. And we are given the coefficient of friction, it's 0.2. They said it's the same. So now we're going to say the work done by the non-conservative force is the change in kinetic plus the change in potential. We know work done by non-conservative. How many forces are non-conservative? It's just one. So we're going to say work done by friction, which is just frictional force, delta x, cos of theta. We know this is 5. We know this angle is 180. But how about this? We do not know this. And to get that, it means this time around, you must know the normal. So it means you have to resolve the force of gravity into components. So it's going to be the Fn here. And we'll have the Fg. The Fg will be there due to the slope, which means the angle here, it is the same as the 12 degrees. Why are we doing this? We want to get the normal. So it means we have to use tail to head. So we're going to have tail to head. And from there, tail to head. So we have how many heads? 2 heads and 2 tails. So that is, so this will be, since it's perpendicular, then it will be our FG perpendicular, and that will be our FG parallel. So we have components actually of FG. The first one is FG perpendicular. Second one is the FG parallel. And since these are the components of FG, it means FG must be used inside. One uses sine and one uses cos. You look at the angle is 12. This is the opposite. So it means this is adjacent uses cos 12, and this uses sine 12. And what is FG? FG, it's mg. So it will be mg cos 12, and this one will be mg sine 12. So we can actually know the magnitude of the two. Now here, but what do you want? We actually want to know, remember we want to get Fk, and Fk, it's mu k times the normal. So it means you have to get the normal force there. And what is the normal force there? The normal force is the vertical force on the object. And since the object is moving up the inclined, it means normal force and Fg perpendicular are in equilibrium. And we know that forces that are in equilibrium always, the net force is 0. They are balanced actually. So to do that, it means this will be, we're going to say the net force, it's 0 for the vertical force because the object is moving horizontally. So normal is positive, Fg perpendicular is negative. So we're going to end up saying normal minus Fg perpendicular is 0 because these are the vertical forces. So normal equals to Fg perpendicular. And what is the Fg perpendicular? Fg perpendicular, it's mg cos 12. I believe you're following. And what is the m? The m is 2. 9,8 cos of 12. So let's get the answer. So this will be 2 multiplied by 9,8 multiplied by the cos of 12. So this will give us 19.17. 19.17 Newton. But we want frictional force, so this will be Fk, it's mu k times normal. What is the mu? 0.2. Normal, we know it's 19.17. So we're gonna say 19.17 multiplied by 0.2. This will give us 3.83. 3.83 Newton. Now we know the frictional force that is acting there. Okay. Now to do that, I hope you are now following mg cos, yes? So now let us now continue with our work. So since we know the frictional force, we can now calculate the work done by the non-conservative force, which is just the work done by friction only. So now let's do the calculations. So we'll have the work done by the frictional force, which is the non-conservative. What is the frictional force? We know it's 3.83. I'm using this approach. Delta x, it's 5 cos 180. The angle between the frictional force and the displacement. So we're going to have 8.83 multiplied by 5. This will be negative 19.15 joules, which is the same as the work done by non-conservative. And now we are going, remember I want to calculate the final velocity. So we will do it like this. So we'll have work done by non-conservative force, work done by non-conservative force, change in EK, change in EP. Apology. We know the work done by non-conservative force, it's minus 19.15. We just got it now. This is half, kinetic final half times mass is 2. Final velocity, we know it's 0. It's this one. Minus half, mass is 2. Initial velocity, we know it's 6.25 squared. Plus potential, it's mgh. Remember, it's mgh, but we want mgh final minus mgh initial. We spoke about this. What is the mass? 2, 9,8. What is the height final? Is we don't know. It's what we want is the h minus 2 into 9.8. What is the height initial? 0. So we're going to have minus 19.15. This guy will become 0. And we're going to have minus 0. Actually, let's say 6.25 squared. This will give us minus 39.06 plus 2 multiplied by 19.8. This will give us, I'm saying 2 multiplied by 9. This will give us 19.6 H. This guy will be 0 here. So we'll transpose these values. This side is going to be negative 19.15 plus 39.06. So this will give us 19 19.91, which is the same as 19.6 as the age. So we divide there by 19.6 and we divide there by 19.6. It will actually give us the height. So we're gonna say 19.6. Oh, sorry guys, it will be 19.96, not 19.6. My apology. 39.06 minus 19.15. It says 19.91. Oh, 19.91 divided by 19.6. Okay. So this will give us a height of 1.2 meter. But now let me confirm this with what I was talking about. I just want to check something. This is 12. It was a displacement of 5. Sine 12 opposite over hypotenuse. 5 sine 12. 5 sine 12. Which is, it's actually 1 point, due to the rounding, this 1.039 something, which is actually 1.04. You see, that is roughly same as that. Maybe it's due to the rounding or when we are calculating the work done by the non-conservative force. That's why I was just asking myself, why do we have to go this long if we know that it has moved the distance of 5 and we can count? Anyway, it was the question. Let's not argue. So this is the answer anyway. I believe, guys, you're actually following. Yeah. Then let's move on. Let us move on. Let's move on to the next one. However, this one, due to time, I'm not gonna do it with you. I'll just give you some hint so that you try to do it on your own. You just pause the video and you try to do it on your own. A 6 kg block slides. A 6 kg block slides with a constant velocity, and this is very important by the way, I shared. A 6 kg block slide, guys. Slide with a constant. These are very important. Like, these are very important questions, guys. When they say constant velocity, what does that mean? They mean that the initial velocity and final are actually the same. Obviously, means acceleration is 0. There's no acceleration, because acceleration, it is the rate of change of velocity. So the changes in velocity over change in time, this acceleration. So if we say there's constant velocity, means from here, the final and the initial are the same. So it means final and initial velocity is the same, so acceleration is 0. It slides with a constant velocity of 4 on a horizontal surface, just here. It hits a rough surface. It hits a rough surface, causing a constant force of friction of 15. So it means this 15 is the one that is taking place at the inclined. No. I apologize. It's not the one at the inclined. It hits a rough. So it means this object was just moving at the speed of 4. Suddenly it reaches a rough surface, or it's there. It means where there's now a friction. So it means even though it's moving at a constant, this will now become an initial velocity. Then it hits a rough surface, causing a constant force of friction, frictional force of 15. We are now given a frictional force of 15. The block slides 2 meters, under the influence of this force, which is the force of friction, until it moves up and inclined. It means up until here, which makes an angle of 30 degrees with the inclined, with the horizontal as indicated in the diagram. So it means the frictional force, according to what they said, it's up until here. Because they say the block slides 2 meters under the influence of this force until it moves up in an inclined plane, which makes an angle of the yes, 30 degrees. Then the blocks move a distance delta x on the inclined plane before it comes to rest, before it comes to, it means this final velocity is 0. So draw a free body diagram to indicate all the force that are acting on the block when moving on the frictionless inclined plane. So it means from here to here, there's no friction. So they want to know, you draw a free body diagram here. So you know how many forces are going to act there. I believe you'll get 1, 2, only 2 forces. Only 2 forces. Because it's just sliding. There's no force applied. There's no friction. Right. Then the second question says, show that the speed of the block at the start of the incline is 2.45 meter per second here, up until here. They just said show. They did not say which formula you should use. They did not specify the formula to use. So there are many ways to skin a cat. Since they did not specify which formula to use, we can use the equations of motion. Or we can use the work energy theorem. Or we can use the work done by the non-conservative force. It's just that the initial height and the final height would be 0. So to get the answer first, we have the initial. The initial is 4. We have we want the final. And we have delta x. It's 2 meters. Oh, by the way, I forgot. I was thinking, no. Yeah, it means if we use the equation of motions, we're not gonna get the answer, because remember, this object was just moving at the constant. If we say acceleration is 0, it will be wrong. It will be wrong. No, I was thinking because we do not know the time and we do not know the acceleration. Because let's check. Let's check, because if we use, no, we cannot get the answer. We cannot get the answer. So it means you have to use work energy theorem. We have to use the work energy theorem. Unless if we do this. Now I remember. Let's identify the force that are acting here on the 6 kg when it was on the rough surface. Remember, it was just sliding. Now I remember. So it means now we're gonna say the only force that is acting here, especially for the horizontal one, would be just friction. So it means if we were to calculate the F net into MA, the net force here for on the horizontal will be minus 15. Why minus 15? Because moving in the opposite. The net for the horizontal will be minus 15. Mass, we know it's 6, so we can get the acceleration. So let's divide minus 16 by 6. You understand why I said it's minus, ne? So it's 15 divided by 6. This will give us an acceleration of 2.5. Actually, it will be a deceleration. So it's negative 2.5 meters per second squared. So if we know this, then now we can use the equation of motion. So we can say Vf squared is Vi squared plus 2a change in x. And we know the Vi is 4. It was moving at the speed of 4. Acceleration, it's now negative 2.5. We cannot put the 1 of 0 because it's going to change. Displacement, it's 2. Then we're going to have 4 squared, which will be 16. 16 plus into 2 times negative, okay, let me just say minus here. 2 times 2.5 times 2. So this one will give us 6. Then we make the root of 6. If I'm not mistaken, square root of 6 is 2.45. Yes, 2.45. Second, so it means it travels speed of 2.45. We got it? That is not the only way. That is not the only way, guys. That is not the only way. Remember I said we can still use work energy theorem. We're still going to get the same answer. Because if you're using work energy theorem, the only force that is, so we're going to say work net is the work done by normal plus the work done by friction plus the work done by FG. This is not doing any work. This is the only one which is doing work here. So it's also not doing any work. So it means you see that the friction will be 15. Delta X will be 2 cos 180. So it will be how much? Negative 30 joules. So with that, we can say the network done equals change in kinetic energy. So we know it's negative 30 here. This is half mvf squared, half mvi squared, minus 30, half, what is the mass? 6 mvf squared, half 6 initial, what is the initial? 4 squared. So it's minus 30. Half of 6 is 3. So this would be 0.5 by 6, 4 squared by 16. So this would give us 48. Let's transpose 48 to the right-hand side. It will give us 18. Let's divide everything by 3. And divided by 3 will be 6. You see, when you put the square root, the root sign, it will still give us 2.45. Many ways to skin a cat. Right, then now, the next question, it says, determine the distance the block will move up the inclined before coming to rest. So it means before the finals, if the speed is 0 here. So we know the initial is 2.45, then now we can calculate this delta x. So I want you to go through this question and calculate the delta x. Sorry, I apologize, guys. You go through the question and you calculate delta x on your own. So we know the initial velocity is 2.45. We know the final velocity it's 0. They told us it is 0. before coming to stop is 0. And there's no friction. There's no force applied there. There's no friction. So what are we going to do here, guys? Is that we use work energy theorem, or we use the other formula, the law of conservation of energy. So what we're gonna do is to say, okay, the initial here, it will be the initial now. It was the final, but it will be the initial is 2.45. Now the final here, it's 0. And ladies and gentlemen, here would not know the height final. The height initially it will be 0. So what we can do, it's either if we calculate the height final, we can know this. But when we use this formula, this one, non-consecutive, change in EK, change in EP. There's no frictional force, there's no force applied, means the work done by non-consecutive is 0. So we know this half mvf squared, half mvi squared, mgh final minus mgh initial. Then now we can do the substitution. Half of, okay, the mass is 6, is still 6. Final is 0 because it will come to rest. Mass is also 6. Initial will be 2.45 here. Plus mass is 6. G is 9.8. We do not know the height final. Let's make the height final here, HF. Mass is 6. G is 9.8. And what is the height initial? 0. So you see that from our calculation, this expression here will be 0 because the final is 0. And this also will be 0. So what are we going to remain with? Okay, let me just use this 0 equals to, so you're gonna have 0.5 by 6 by 6 by, oh, sorry guys, supposed to say squared here. By 6 by 2.45 squared. Zero 0.5 multiplied by 6 multiplied by 2.5 squared. This will give us negative 18.01 plus 6 multiplied by 9.8. This will be 58.8 as the height final. I'm referring to this. This one is 0. So if we transpose negative 18.01 to the left-hand side, this will be 18.01. It will be 58.8 HF. Now we divide both by 58.8 and 58.8. So what is the height final? So we first determine the height final. So this will be 18.01, 18.01 divided by 58.8. So it means the height here will be 0.31 meter. So it means we have the final height is 0.31 meter. And since this is a right angle triangle, we have the final, we have the angle, so we can get it by using sine. So this will be the opposite hypotenuse. So we're gonna say sine 30. It's opposite of hypotenuse. What is the opposite? Opposite is our HF, which is 0.31. Hypotenuse is our delta x, so it is over 1. Let's cross multiply. So this will be delta x sine 30, 0.31. Then we divide it by sine 30. Okay, so it means that delta x now will be 0.62, if I'm not mistaken. 0.31 divided by sine 30 is just 0.5. So this will be 0.62 meter. So it's 0.62 meters. Another way would be, because we're using non-conservative force. Okay, it's fine. I understand. So if we do not want to use this, we can also use work energy theorem. We can also use work energy theorem to actually calculate delta AH, delta X, without having to do this. Remember, what is delta X here? 0.62. Let's confirm it by using the work energy theorem. With the work energy theorem, we have to first calculate the net work done on object. So we can say work net, sorry, it's change in EK. So change in EK, we can get it, it's half MVF squared minus half MVI squared. So we can calculate this half into 6. This is 6 point, not 6.25. The initial it's 2.45, I mean to say. The final, it's 0. The initial mass into 6. The initial is the one which gives us 6 point, not 6 point, sorry, I apologize. 2.45 squared. So this will give us minus how much? I think we got it there. I think it's minus 18 point something. Okay, let me just confirm it. 2.45 squared. Okay, then this will give us minus 18.01 joules. This is the work net actually. So now, since we're using, then we're gonna say how many forces are actually acting here. Is the normal? There's no frictional force. It's only force of gravity. So it means when I look at this angle here, what is the angle? 30. So here, where is the object directed to the right? So this is the MC upwards. So we want the angle between delta X and, I'm solving using that approach of not determining the components. So since the angle here is 30 and here the angle is 90, what is the angle between? So it's 90 plus 30. So it means we're gonna say the only work net here, it will be work done by Fg because the normal is 0. So Fg, it will be Fg delta X cos theta. Fg it's mg, so it's mg delta X cos theta. What is the mg? The m it's 6, sorry. The g is 9.8, but we do not know delta X is what you're looking for. Cos of, what is the angle between? 120. So let's work out 6 by 9.8 by cos 120 and leave delta X. 6 multiplied by 9.8 multiplied by cos 120, cos of 120. This will give us negative 29.4, 0.4 multiplied by delta X, because there's delta X here. It is. So we have calculated work net. We're going to say work net is equals to, what is the answer that we got? Minus 29.4 delta X. And guys, what is the work net all in all? It's negative 18.01. We got it. So it's minus 29.4 delta X. So we divide it by negative 29.4 and we divide it by negative 29.4. And this will give us our delta X here. So now to respond to that, so we're gonna say 20, what is the value there? 18.01 divided by 29.4. Then this will give us roughly 0.61. It's because of the rounding. is because of these negative 18. If we have left this number, then the answer will still be the same. It's 0.61. It says 613, so which is just 61 meter. The answer is different because of this value. We have rounded it to the nearest. Even the 24.9, we have rounded to the nearest. That's why the answers are a bit different, but it has to be the same. So delta x is 0.61. So I believe, guys, you are following. This is actually the end of the session. And kindly like the video, subscribe, and share to your friends. Thanks, guys, for listening. Goodbye.